Hello, today I'm going to present our paper titled A Fully Automated Deep Learning Pipeline to Assess Muscle Mass in Brain Tumor Patients. First, I would like to give a brief background. Glioblastoma is the most common brain tumor, which has a very poor prognosis. Only around 5% of all diagnosed patients survive for 5 or more years. Low skeletal muscle mass has been linked with lower survival in cancer patients, and temporalis muscle thickness has been identified as a proxy to measure skeletal muscle mass. However, to manually outline the muscle is time-intensive and prone to rater inconsistency. Thus, we wanted to develop an end-to-end automated pipeline to segment temporalis muscle and calculate its cross-sectional area. Convolutional neural networks have been used in a variety of medical image segmentation tasks, including muscle segmentation. UNIT, which is a neural network designed specifically for medical image segmentation, has been used to segment various muscles successfully, such as thigh, pelvic, or muscles of the chest. And a variety of imaging modalities have been used, for example, magnetic resonance imaging, computed tomography, or digital mammography scans of the breast. To segment temporalis muscle, a few previous approaches have been developed. In one paper, a region-growing algorithm using intensity similarities among neighboring regions as criteria to segment facial muscles in 3D was developed. In another study, range-constrained thresholding was used to segment temporalis muscle, and adaptive morphological operations were then applied to remove remaining brain tissue in 2D MRI. However, no previous work used convolutional neural networks, or UNIT, to segment temporalis muscle. Thus, we wanted to see if this was feasible. In our previous work, we have developed a deep learning tool that automatically segments and quantifies temporalis muscle in 2D, with a dice overlap score of over 90%. We have also shown that temporalis muscle cross-sectional area is strongly associated with overall survival and time to progression into BM patients. In our current work, we aim to use a clinically inspired heuristic for slice selection. We wanted to use eyeball as a landmark for selection of an axial plane for temporalis muscle segmentation. In previous work, we had to manually select the slice in which we wanted to segment the muscle. Thus, we aim to train a deep learning system to replicate this approach, and then to segment and calculate temporalis muscle cross-sectional area. This is an outline of our fully automated pipeline. We first take a 3D brain MRI scan in NIfTY format as input, and slice, pre-process, and convert the images to PNG format. Once we have the 2D PNG files, we feed them into the first pre-trained neural network to segment the eyeball. The code then looks at the segmented eyeball areas from different slices for each patient, going from top of scan to bottom, and picks a slice once the area is over a certain threshold, which outputs one slice per patient at a level slightly above mid-orbit. We then feed these 2D slices to the second unit, pre-trained to segment temporalis muscle, and then calculate its cross-sectional area. The output is an Excel spreadsheet with patient numbers and corresponding muscle areas. Now I will briefly go through the methods. For training, validation, and test data, we used 4 datasets, 1 in-house glioblastoma patient dataset, and 3 external publicly available datasets. To train both models, we have used over 300 images, which came from over 100 patients in each. For image preprocessing, we have done bias field correction and z-score normalization, which are important when working with MRI imaging. We have also resampled and resized the images. For segmentation, we have done manual segmentation of both eyeball and temporalis muscle using ITK Snap software. For the model, we used an existing implementation of a 2D unit in Keras and TensorFlow. The unit architecture consists of symmetrical contracting and expanding paths. The contracting part is made of 4 downsampling operations, which are blocks of 2 convolutional layers and 1 max pooling layer. The contracting path is made of 4 upsampling operations, each of which have 1 upsampling deconvolutional layer followed by 2 convolutional layers. We modified the unit further by adding batch normalization after each convolutional layer and 2 dropout layers to accelerate training and control over fitting. The output layer is a 1-by-1 convolution with sigmoid activation function, which assigns values in the range from 0 to 1 to each pixel. The final segmentation is obtained by binarizing the probability at the threshold of 0.5, mapping each pixel to either muscle or background class. For training, we have used a dice loss function, which is based on a dice overlap coefficient and has been proposed in tasks where there is a class imbalance, where the negative examples, or the pixels belonging to the background, significantly outnumber the positive examples, or the object to be segmented. Cross-entropy loss, which is used by standard, is based on accuracy, whereas dice loss considers both false positives and false negatives as of equal importance. Thus, it is less prone to the class imbalance issue. Also, in our previous work, where we have trained a unit using only our in-house dataset, we compared the performance of the model using 3 different loss functions: binary cross-entropy, Hausdorff loss, and dice loss, and we have shown that the model trained on dice loss outperformed the other 2 models. We have further optimized our model by changing the number of epochs and steps per epoch while observing the training metrics. We then wrote code in Python to combine multiple steps and the 2 pre-trained models into the final, fully automated pipeline as outlined previously. To evaluate the accuracy of the pre-trained models, we used an unseen test dataset and compared the ground truth image with the predicted segmentation, using overlap measures such as dice coefficient and Jacquard index. We have also looked at precision and recall and assessed Hausdorff distance, which is the greatest of all distances between a point in one set and any point in another set, and is often used to evaluate segmentation accuracy as well as the overlap measures. To evaluate slice selection in the automated pipeline, we looked at the percentage of slices selected at the same level as the human evaluator, as well as within 1 or 2 slices. The human evaluator was asked to select 1 slice above the mid-orbit. We were able to produce accurate segmentations of both eyeball and temporalis muscle, and you can see the example predictions on the screen. Both models had a high dice coefficient of 0.9 and Jacquard index, which was over 0.8. The precision and recall for both models was similar and around 0.9. Finally, Hausdorff distance was small, 2.89 for eyeball model and 1.89 for temporalis, better than previously achieved for spine, masticatory, and lower abdominal muscles. Thus, these results show that the predicted image closely resembles the manual segmentation. Looking at the results for slice selection, although only 13% of automatically selected slices exactly matched that which was manually selected, almost all of the slices, 96.1%, were selected within 2 slices of the human evaluator, showing that our model can select a slice at the desired anatomical level in most patients. Thus, with this work, we developed a novel fully automated approach that accurately assesses the cross-sectional area of temporalis muscle from 3D brain MRI scans. Our segmentation accuracy is in congruence with previous approaches, as the 2 other methods discussed before, which segmented temporalis muscle, had overlap scores of 0.78 and 0.9 comparable to our score of 0.9. We have shown that there is a potential role of deep learning in muscle quantification and assessment of muscle loss in GBM. Nonetheless, there are some limitations to our current work. First, some structures other than the eyeball are segmented in some patients, which might lead to incorrect slice selection for these patients. Furthermore, the full pipeline was only tested on 61 patients from 1 dataset. Thus, this work needs to be extended in order to validate our model. Finally, I would like to thank my colleagues who have worked on this project. Elami, who has done work in all stages of the project, Dr. Matt Williams for continuous input and feedback, Dr. Jarong Shen for producing eyeball segmentations, as well as Dr. Andrew Ho and Ms. Lily Paksat Shahabi. Thank you for your attention.